Okay, so for your homework tonight, we are going to start talking about section 2.4, so that way we are ready to start section 2.5 in class next time. And 2.4 is all on exponential functions, which you should have seen in Algebra 2 and probably Algebra 1 before. Okay, so first we have to talk about what is an exponential function. So an exponential function has a format that looks like this. So it's y equals a times b raised to the x power. So it's called an exponential because the variable is in the exponent. Okay, so there's two different things to know about this. The initial value is a. So the initial value is when x is equal to 0. So if you plugged in 0, any number raised to the 0 power goes to 1. So the initial value will always be a. And then the growth factor is b, the base of the exponent. So we have two situations. We have exponential growth and exponential decay. So exponential growth is when something gets bigger. So that happens when b is greater than 1. Now something is going to decay or decrease when the b value, the growth factor, is between 0 and 1. So we have to think about growth and decay as like percentages. So we have to remember that 1 is equal to 100%. So basically, if your growth factor is bigger than 100%, it means you're getting bigger, and if it's less than 100%, it's getting smaller. So let's talk about what exponential functions actually look like. So we want to make a graph of the function 2 times 3 to the x. So let's make a table. So question 1 asks us to figure out what f of 0 is. So that's the initial value, f of 0. So f of 0 is going to be, the initial value is always a, which is the coefficient out front, so that's going to give us a 2. Okay, so let's find a few more points to see what happens. Let's plug in 1. So if we plug in 1, we get 2 times 3 to the first, which is 3, so that gives us a 6. If we plug in 2, we get 2 times 3 squared, which is 9, which is 18. So let's also talk about what happens when we plug in negative numbers. If we plug in negative 1, we get 2 times 3 to the negative first, which is the same as 1 over 3, which gives us 2/3. So let's use those points to sketch a graph. So we know that we have a point at 0, 2, a point at 1, 6, and a point at 218, which is really high off of our graph. So we'll say it's like up here. And then if we go to negative 1, it's at 2/3. So we're like right there. So what happens is an exponential looks like this. So this is an exponential growth function. We can see that it is growing as it goes further to the right along the x-axis. So now we want to talk about what the domain is. So domain is all the possible x values. So if you look at an exponential, you want to think about what x's could I not plug in? Well, you can have any number as an exponent, positive, negative, and 0, so the domain is all real numbers, which has that funky R symbol. And then we want to talk about the range. So no matter what kind of exponent you give to a function, it's always going to have, as long as the base of it is positive, it's always going to come out positive. Negative exponents still come out as positive answers. 0 comes out as a positive answer. Positive answers come out as positive answers. So our range is all of the positive y's, which we can write as y as greater than 0. So something to take note of here is it does not hit 0, does not hit the x-axis. So then asymptotes. So you've probably heard about asymptotes in Algebra 2. An asymptote is a line that the graph approaches but never actually touches. So for an exponential, that's going to be the x-axis, which is the same as saying the line y equaling 0. So y equaling 0 is the equation of the x-axis. So exponentials get really, really, really close to 0, but they never actually touch the x-axis. They never actually equal 0. Okay, so let's actually do some examples with some exponential functions. So we might need our calculators for this, and so we want to have them handy. So let's read through it. We say that the town of Centerburg is suffering from a decline in population. So that word decline might be important. demographer, or a demographer, however you want to say it, has predicted that under current conditions, the current population of 28,500 will decrease by 2% each year over the next decade. However, a manufacturer claims that a new factory will reverse the trend and cause the population to grow by 4% annually instead. So the first thing we want to do is we want to create equations to describe the population of this town as a function of time, and we want to create two functions. So function f is going to be by increasing by 4% with the new factory, and function g is going to show a model for the population decreasing, so that's without the new factory happening. So if we are growing, that means we're going to keep the original population each time. So we're going to keep our 100% and then increase by 4, which means our growth factor is going to be 104%. Now we want to change 104% into a decimal. So remember, you move the decimal place 2 points over, so we get 1.04. So if we're talking about function f, our growth factor b is going to be 1.04. So now we just have to talk about the initial. Well, it told us that the initial population of Centerburg was 28,500. So that means our function f of x is going to be 28,500 times 1.04 raised to the x power. So now we'll just do the same thing for g. So g is going to have the same initial population because we're talking about the same town. So that's 28,500. But now we are decreasing by 2%. So we're going to start with that 100% and then go down by 2% every year. So that means we're going to be left with 98% each year. So for 98% as a decimal, we're going to write that as 0.98. So that turns our g function into 28,500 times 0.98 raised to the x power. Okay, so there's part A done. We created our functions. Now on to part B. We want to compare the predicted populations after 10 years. So we need to plug 10 into both of our functions. So we're going to do f of 10 and g of 10. So now this is where we're going to need our calculator. So I'm going to go to my calculator and type in f. So I'm going to go 28,500 times 1.04, use the caret key for my exponent, and plug in 10. I get out 42,187 if I round. Now if I do the same thing for g, all I have to do is change that 1.04 to 0.98. I get out a population of 23,287 people. So to compare them, if we get the new factory, we have a significant growth in the population, whereas if we don't build the new factory, the population goes down by about 5,000 people. Okay, so here is our last example for just exponential functions. We'll actually start creating models of our own in class next time. So this is money. Everyone loves money, and this is about a savings account, which is important because savings accounts are important to know about. So in this example, we have $2,500 is invested in an account with a 5.3% annual yield. So if it's yielding something, it means that it's growing. So to get our growth factor, what we're going to do is we're going to start with our initial 100%, and we're going to add 5.3% each year. So we have 105.3%. But we want to use that as a decimal because you can't put a percent into an equation. So what we're going to do is it's going to become, moving the decimal point 2 points over, 1.053. So now we want an equation for the balance A after t years. So that just means write a function. So our initial value is how much we initially invest in the account. So our initial is going to be 2,500. We just found our growth factor to be 1.053. And our variable is t, so that goes in the exponent. So then to find our balance after 7 years, all you do is plug 7 in for t. So we're going to do a of 7. So again, you go to your calculator, and all you have to do is type it in. So 2,500 times 1.053, all raised to the 7th. That's going to give us 3,588.71 cents. So now it's asking us to think about what the value associated with -2. So again, we plug in to find a of -2 of our function. So again, typing that into our calculator, we get 2,254 and 67 cents. Okay, so t being -2, so remember t is time, and it's time in years. So -2 would mean 2 years prior to the investment. So in this time, in this example, negative variables don't exactly make sense because you can't have negative time, first of all, and it's talking about what happens before the investment is made. So your growth rate isn't applying to the money at that time because it's not in the account.